Okay, so hi everyone. Today is the first real class. Let's say last time was mostly an introductory part, and today we're gonna actually dig into the topics. Today's topic is mass spring systems, so we're gonna dive a little bit into these modelization for objects. And of course, now well, the first thing that we think about when we are talking about springs is something like this, but this is really not only about something that simple, because spring system can be used also to model something a little bit more complicated, such as, for instance, cloth, deformable elastic objects, ropes, and all the stuff that you might end up finding in when designing and programming games. So the first thing that we want to discuss in this session is a brief recap on the very basic physics behind the projectile motion, which is gonna be the first part, and the description of how we gonna present the movement of the objects. So first off, we usually think about a particle with negligible mass, and it is described by its position x that is changing over time, and this particle is characterized also by velocity and an acceleration. Now here we have a small sketch of the trajectory of the projectile, and the velocity normally is the vector associated to it. And in the relationship between these quantities is given by a differential relationship. So in this case, we have that the velocity can be derived from the position by using a derivation in time. And if we want to go backward and we want to obtain the position from the velocity, we will need to integrate over time. And all these, something that we're gonna learn how to do it in using numerical approaches, because typically this is not possible to do it in an analytic way for most of the cases that we are gonna encounter. And the basics for understanding how a particle or an object is moving around is referring to Newton's second law, for which force is proportional. So the acceleration, is proportional to the forces that we are applying to our object. And one example of that is clearly like gravity, that in our reference system is pointing downwards as it should be. And here we just put a picture of Newton just to make sure that we remind about that. So what we have is two integral relationship. One is for the velocity, that is the derivation of the position with respect to time, and also acceleration, which is instead the derivative of the velocity with respect to time. And normally for a projectile motion, we can actually write an analytic solution, and that analytic solution will look something like that. And as we can see, the projectile is accelerating over time, and with the constant acceleration which is given by gravity. And from the beginning, it moves with the initial velocity that we have given to it, which is v0, and from the place that we have set the object in first place, which was x0. In this case, as you can see, the mass doesn't matter, because it's always the same object that is moving, and gravity is an intensive force in the sense that is proportional to the mass. So the bigger is the object, the larger is the gravitational force that we have with respect to it, which means that we can cancel it out in our equation. So independently from the mass of our object, of our projectile, the movement of the object will be always the same. Of course, this analytic integration is only possible for very simple force function like the one of the gravity, which doesn't change in space, doesn't change in time, and it's very, very simple and very, very well behaved. But in general, this is a little bit more complicated to do with any random and possible force. So our goal is to define how things and our objects move around at the given time, and typically both the acceleration and the velocity are provided in the form of a relatively complicated function. So the analytical solution that we saw before is typically not possible, or it's very complicated to achieve. So our solution for this is to discretize space and time and try to integrate this relationship numerically in order to obtain the trajectory over time. So just to have a brief idea and bird eye view of what we are going to do during these classes. First off, the overarching goal is to try to simulate deformable objects using a mass spring systems and using this kind of modelization. To do that, we're gonna first have a look at what is a model, a physical model for springs, and how we relate, we compute the forces that are related to springs. And later on, we're gonna have a look at how we are integrating ordinary differential equation, which are the one that we saw before, for instance, for the velocity and for the acceleration. And depending on the method that we are using, of course, we will have different problems, and we're gonna dive into the benefits and pros and cons, essentially, of all of them. And finally, which is the more, let's say, active part, we're gonna see how to implement this in a practical environment, in a practical game whenever it's needed. So first off, we're gonna have a look at mass spring systems, and as well could be told, it's composed by masses and springs. So usually, what we do is what we have in reality is that we have objects that are extended in space, that have a certain distribution of their mass in their bodies. For instance, if you can think about your own body, the mass is not uniform, is distributed in different places, and if you want to model this in a video game, you will also need to take this different density of your body and distribution of your mass whenever you're modeling this. So typically, a simpler approach to that is try to discretize the mass of an object into a small number of places where we concentrate the mass. For instance, we're modeling our body with a few points, for instance, our head, our torso, 2 legs, and 2 arms, for instance. And this will give us a much easier and a much lower dimensional system to deal with, which is going to be much more practical to work with and to integrate with. Of course, it's always a trade-off between the accuracy of your simulation and the speed of it. So whenever you are discretizing, you can discretize a body using a single point. So let's assume the body is just a single point with the mass of your body, and that's gonna be the simplest and fastest way to perform calculation. But of course, you're gonna lose all the details related to the shape of your body and the how it deforms, for instance, whenever it's interacting with other rigid bodies. And this modelization can be used both for elastic objects, to some very limited extent to fluids, and also to other inelastic objects. But of course, we're gonna need to add more and more assumption into the modeling as we proceed. So normally, the interaction between 2 different points in our discretization are based on the internal forces that interact between each other point. And all other forces that are external to the body are what we define as external forces Fx. And here we include gravity, we include wind, whatever for external forces to the body needs to be modeled in this way. If you are modeling a collision, for instance, these will come as an external force with respect to a given point, and not as an internal force. Overall, we can compute the force acting on the individual points, summing up the internal forces that are acting on a single point, in this case I, plus the external forces. Should be noted here that internal forces are antisymmetric, meaning that if we are the internal force that acts on the point I because of point J is gonna be exact and opposite, the same as the internal force that is acting on body J because of body I. And these gives us an important relationship, which is the fact that the sum of all the internal forces in our set of points that are composed with the body, that are composing the body, will give 0 as a sum. And this actually is something that you might want to check in your simulation, because that gives you also an idea whether your simulation is going in the right direction or not. So that could be actually a good sanity check. But let's do a quick example here. So let's assume we have this pentagonal object that we want to discretize. So first off, we need to sample the mass in some given points. Let's say we provide 6 points, and given we have an object that on average has a mass that is m in total. So let this be maybe the weight of your body. And what we want to do in first approximation is that given an n number of points, we discretize the mass evenly across the different points. So the distribution of the mass is uniform. So in this case, what we get is that each individual point has exactly nth part of the total mass per each point. And in our simulation, what we are going to do is to try to simulate the motion of each and every individual mass point, which has a much simpler dynamic than the entire body, in which we have to consider, for instance, the rotation of the body, or any kind of deformation needs to be explicitly modeled otherwise. So, sorry. So now we completely forget about the original object that we were trying to model, and we only left with our concentrated mass in these points. So this is meant to be a physically based model. So we also want the Newton's law holds, and here you can see how the sum of the forces is proportional to the mass of the individual point and to the acceleration that we are going to provide. And now the question that is, how do we know how to compute the external forces, because those are gravity, those are all the forces that are acting on the body before we discretize it. And now the question is how we compute the internal forces in our body. So we assume that this body is not completely rigid, which means that we allow the individual mass to move with respect to each other. And in order to model how elastic this body is, we're gonna rely on springs. So what we're going to do is that we're going to connect each point to its closest neighbor, and we're gonna model the relationship between the deformation and the force that is acting internally using Hooke's law. So Hooke's law states that the forces needed to extend or compress a spring is proportional to the distance that we are using for compression or extension. So typically we can have, this is like, of course, an approximation, and this is a behavior that we need to say, this modeling assumption we need to keep into account whenever we are computing our simulation. So the basic state, the return to the rest state, is something that you have when you have an elastic behavior, which is completely different from a plastic behavior, where the current state is kept after the deformation. So Hooke's law will not hold in a plastic regime, and it will certainly not hold in the case of fluids, because of course they don't have a given shape. So whenever you move an object, it's gonna indefinitely move, and there will be not let's say returning force in the flow in the fluid to the initial position. And of course we have and nothing is like black and white. We have a grade of shades of gray, let's say. So we need always to assess up to which extent these assumptions hold for our simulation. But first off, let's have a look a little bit about at the simple and regular spring. So each spring, as that you have intuitively seen also in real life, let's say, it's characterized by a certain stiffness, which is denoted by K, and it has an initial length, which is capital L. Now, whenever we deform it, either by compression or by extension, we get it to a different length, which is small l. And as we mentioned, the force is linear and proportional with respect to K, with respect to the deformation. So here what you see is that the difference in the deformation is given by the current length by minus the original length. And it is important to notice, it is important to notice that there is a minus in front, and that is because the force typically is opposing the deformation that we have provided. So whenever we are extending a spring, then the force will tend to compress it, and as soon as we try to compress it, then the force will react to that and try to extend it back to its regular position. And of course, this is a very simplistic behavior, and someone might wonder, how good is this approximation for actual things? And I put it here a small diagram here, and it's interesting to see that this spring model also holds for a number of materials and things that will not necessarily model a spring. So for instance, these are two blocks of aluminum and steel, and if we try to pull them apart, you can see that in this area the behavior of the two metals is actually linear with respect to the deformation. Of course, like the deformation is extremely small because it's metal, so it's you can think about it as an extremely rigid spring. But in practice, to some extent, even metals do behave like springs to a certain extent. Then the rest of the curve that you see here is that what we call a plastic behavior. So then now, once you pull strong enough, essentially, what we have is that the material is permanently deformed, and we are not able to recover the initial state. So in this regime, of course, we are not able to use let's say this spring model to model a piece of metal, essentially. So the force that we get from the spring is always a directed force, and it's always in the direction of the deformation. So usually we model it at the endpoints of the spring, and this is gonna give us also an hint how to deal with that whenever we are implementing this. And in vector notation, we can write this using the same expression as before, but now what we have added here on the side is essentially the direction of the velocity, of the deformation. And as you can see, we only have the difference between the location into the 3D plane, into the 3D space, that where we have the spring, and L is just the, let's say, the absolute value of the difference between these 2 points. So whenever we are modeling it, it's let's say we always have a force that is gonna pull in the opposite direction and along the direction of the spring. This, of course, is just the starting point, because we are looking at one single spring and 2 points. So what we're gonna do now is extend this to a set of springs. So in this case now, we not only have one spring, but we have several, and potentially every spring is described by its initial length and by its stiffness, and in the simplest case, all these quantities are the same, but that's not absolutely given and that's not necessary as well, which means that we can assign to the individual springs a different stiffness, and of course this will have an impact on the way the body will react whenever forces are applied. So for each and every point that we are going to model, what we need to do is that we need to calculate the internal forces with respect to the individual point. And in this case, all the forces, the internal forces that are acting on these on the central point, which is x0, is simply given by the springs that are attached to that point. So what we're gonna do is just computing for each and every spring the force based on the corresponding stiffness, corresponding deformation, and importantly corresponding direction, because of course it's always let's say a vector relationship. So the forces that are acting on the individual points is gonna be oriented, and whenever we are performing a simulation, then it's important that we sum these forces as as vectors, because of course otherwise the results will not be correct. And once we are done with the sum over the internal points, then we also want to add external ones. So for instance, gravity, user interaction, or any kind of deformation that can be considered. This system, one important thing about this system is that this system conserve its energy, which means that if you deform the spring, it will accumulate energy and will release it entirely without any kind of loss. So if we, let's say, start moving this object will continue moving infinitely, because the amount of energy of this object is going to be always the same, and there will be infinite motion. And as we experience every day, essentially we don't really have infinite motion, because typically what happens is that there are some dissipative forces that are also acting on our body. And normally with these dissipative forces are typically proportional to the velocity and rather than the position. And intuitively you can think about, for instance, the resistance of air, which to some extent can be considered a function of the velocity. So if you're going very slow, you don't really feel the resistance of the air, whereas whenever you start running faster, or you're biking, then you definitely feel the resistance of the air against you that is taking away energy from you. Of course, this is a very simplified relationship. If you were to think about how it works in practice, this is going to be maybe proportional to the square of the velocity or different stuff. But for, let's say, for the time being, for our interest is just to model these dissipative forces, it is important that we mention the fact that this quantity is proportional to the velocity of our object. And this can be used, for instance, to model internal friction or other non-conservative forces that are acting on the system. So the important part is that it removes energy from the system itself. And in the context of simulation, and in particularly game simulation, this can be used as a numerical tool in order to stabilize the simulation and making sure that objects do not behave in a unexpected manner. And these can also be used, for instance, if we want to prevent some, let's say, not prevent but counteract some numerical error that we are making, because I don't know, our discretization is not fine enough, our modeling of the forces is only correct to some extent, because we are not always being absolutely exact in our modelization. And in general, what we get from a single point is an equation that looks like this. So the acceleration of an individual point is equal and to the sum of all the forces acting on that point. And if we put together all the elements that we have seen in the previous cases, what we get is something like this. So here, this equation is just gathering together all the things that we have seen before, and now we're gonna go through each and every term. So the first one, of course, is acceleration, and now it is written in a different way, but if we come back to the notation that we were using before, we saw that v was the derivative of the position with respect to time, and the velocity was the derivative of the velocity with respect, sorry, the acceleration was the derivative of the velocity with respect to time. Then we can combine these two definitions, and we can also write in this way. So you can see that our acceleration is actually the second derivative of the position with respect to time. Then we have, of course, the internal forces that we mentioned before. Now, it should be noted in this case that the the internal forces depend on the current position of the body, because of course the other and all the deformation are related to the position. Yes. So normally it's just because that is dt as a derivative. So usually how you write it is because your operator is something like this that is acting on something. So you might think that is not the, let's say, usually this is just applying the derivative twice, and your derivative is something like that. So you usually write it d square divided by dt square, and not you don't add the 2 on the first d again, essentially. But it's like derived twice anyway. Is that what you were asking? It's okay. Yes. So the question was regarding whether we don't put dt in brackets, just repeating mostly for the recordings. But in general, this is the notation that is used in physics. Essentially, let's take it like this. So there is no. It would add more confusion, mostly because you are adding more and more quantities and parentheses, and one should really think, in my opinion, as the derivative as let's say you're not really dividing by dt square. It's just that you are indicating that you are deriving with respect to that. So to avoid maybe because maybe later you are dividing by some other quantities. So if you use this notation that is slightly different, then this can help you avoid mixing up derivative operation and divisions. Mm, Probably we would understand, but if anyone would read what you're writing, would be more confused than understanding better. So in practice, the biggest issue is that this is more like a convention that people use. So it's not necessarily wrong, but it's just that might confuse people, especially the average physicist will be very confused by such notation. Any other question so far? Yes. Newton notations. I guess yes, but it. Let's say as far as I understood, maybe Felix can confirm that the use of Newton notation in the exam, most likely the exam is mostly, let's say, in the exercise session, you will be given more detailed explanation on what should be, should be there and what should not. And by looking at how the exercises are done, then you will also get an idea on what kind of answers we are expecting from you also in the exam. Right. Internal forces. So we said that they depend on the current position, in the sense that we need to compute the deformation of the or the deformation of the other springs with respect to the current point, in order to understand what is the force that is acting on our individual point. And here also the external forces, we mentioned those are gravity and such, but the important one is that now we are adding the damping forces, and which I have written here in a slightly different way, but as we mentioned before, velocity is proportional, is defined as the derivative of the position over time, so we can definitely write it like that. And this notation will actually come in handy in when we are looking at the way, let's say, the mathematicians community is solving this problem and looking at this problem, integrating this problem. Yeah. So one small things that I want to mention is, and maybe start slightly early, is also start to think about how we want to implement this in a practical sense. So we have, let's say, what we really want to do in practice is that we want to integrate this equation over time, and we assume we know both the velocity and the acceleration. Acceleration is given to us by the Newton law, and what we want to do essentially is to discretize the equation in time, and to do that we can use the Euler integration method that you might have seen also in the game engine design lecture. But for those of you who didn't, I will just recall this. So for instance, what we are going to do is that, since we know that the velocity is, let me just have it a little bit lower, the velocity is given by the derivative of the position over time, then we can approximate this variation in a finite way, because the derivative gives us the infinitesimal variation of the position with respect to time, but we can approximate it by looking at two different positions. So for instance, we assume that our dx is actually a delta x and dt is actually a delta t, so like two finite quantities. And what we get is that we take the position at a given time, we subtract the current position, and we divide by dt, which is the distance between the two instants that we are considering. And from this relationship, we can easily retrieve the next position, which is the position in time, as it is just v dt plus the initial position, which to some extent reminds us of the analytical integration that we were performing at the beginning. And but of course, this is a very useful trick and method that is, although only accurate to the level of discretization that we are using. So if we are considering 2 points in time that are very separate, then the accuracy with which we are modeling the behavior of the body is relatively is diminishing. Whereas if we are considering a very small time, then we are approaching, let's say, the limit of infinitesimally small quantity of time, and in that sense our approximation of the derivative is then better. But we're gonna formalize this later in a moment. So what we want to do is that we want to integrate velocity and position in time using this approach, both to the velocity and the acceleration. And in a computational sense, what we can do is that we can write a different class for the point, so the masses and the springs. So here, what we are doing is that we just have a C++ template. Uh, we have that each and every spring is defined by the two endpoints, by its stiffness and by its initial length. And in principle, we can also store the current length, which could save us some computation, but not so much memory. But it's in any case it could be useful. And one important thing that it's used here is that we are not considering the positions as floating points, but rather to integer that, and we can imagine this as referring to a sort of register with the position of the different masses, and we are just indexing the different positions. And this just because whenever we are computing the mass extension and deformation, one should remember that the sum of the internal forces need to be 0. And if we are inputting directing the value of the position, then we can have some sort of problems. Whereas in general, if we are referring to a common set of position for our bodies, then this should always compute the internal forces in a better way, in some extent. And in fact, whenever we are characterizing the mass points, now we have that the position is indeed, let's say, a three-dimensional vector, and also the velocity and the force that are applied are three-dimensional and are vectors. This force vector is considered to be some sort of cumulator, in the sense that we are computing the individual forces and summing all the different contribution into this term, because then what we are trying to construct here is essentially the Newton's law, and we want to construct the right-hand term of Newton's law in order to compute the acceleration correctly. Of course, we need to characterize this point by also all these other physical quantities, such as the mass, the damping, and so on and so forth. And our simulation loop is gonna look something like this. So for all the points that we have in our system, we first off we will need to remove any force that we computed in the previous step. We can add gravity because we know it's always there and it's gonna be always the same for all the points, and this is clearly gonna be summed up to our force object that we have defined before. And then for each and every spring, we want to compute what are the elastic forces that are acting at both ends. And one thing that is important here is that each and every spring is acting in the same way to both ends, because if you look, let's say the force is only proportional to the length, to the deformation essentially, and it doesn't matter whether we are deforming to the right or deforming to the left, but the forces will be impacting both sides of the spring in the same way. So one good thing about this approach to the modelization is that we need to compute the elastic forces only once, because we only have one deformation for each spring, and then we can add the same force to both endpoints, whereas in alternative approaches we cannot do that, and we need to compute the forces twice, which is arguably less efficient from the computational point of view. Now, once we have evaluated all the forces, what we can do is that we can integrate position and velocity using the Euler step that we described before, and then we are able to update our position and velocity, and then start the loop again. Yes. It really depends on the approach that you are taking. So the thing is that for Euler step, as it is Euler, as it is described before, so that the velocity is given by x t plus delta t minus x dt. As you can see here in this equation, now we can invert and find the position. This equation depends only on the velocity at time t, so on a quantity that you know already before integrating the velocity. So what integrate velocity will give you v t plus dt, right? So this element is not necessary to compute the next position, although one could use more complicated discretization methods, and we're gonna look at that later today or in the next class, in which we can make use of more information in order to provide a better approximation. But in principle, this is called an explicit scheme. We don't require to know already the solution in the next point to compute the solution in the current one. So to some extent, here is really one could integrate first the position and then the velocity, or vice versa, but it's not going to be not going to change the result, at least for the current approach. Other questions? Sorry. Alternatively, which is something that is mentioned in the book that has been possibly suggested in the first lecture, is that we can implement generic force generators, in which essentially these are linked to a single mass point, and then by evaluating the force function, then we can accumulate in the same way that we have described before in the mass. It has as a pro is that it's like the interface of the, let's say, of the generator is simpler and more straightforward. However, you need to have, let's say, a force generator for two different points. So because the spring is the same attached to both hands, so in a sense we need to compute twice the force of an individual spring for each one, for every points that we have in our system. But of course, if we are trying to model a much larger number of points and much larger body, then this could make sense to some extent. Yes. So just one more quick thing before the break is talking about collisions. And in fact, if we assume now that we have a ground plane at y equals 0, what we do is that we need to make sure that our body do not, penetrate the ground in an unphysical way. So we need to enforce that all the body stays above the ground plane. And we compute the new position integrating as we have seen before. Then we need to enforce that the value of y is positive for all the points, and then the spring forces will generate a reaction and internal forces in our body that will, let's say, deform our body according to what is happening in our simulation. There will be a way longer description of the collisions later. One thing that I wanted to mention before the break is that, of course, now I'm using y as the position in space, because I'm assuming that I have a system that looks like this, so I have x and y. But whenever we are moving to 3D, then things can be arbitrarily defined. So let's say some people would prefer to see something like this, and then x, y are the plane, and then z is the distance from the body. Other people would say, like, okay, I have x and y in my 2D plane, so I will naturally extend my third dimension to be z, and both approaches are in general just fine. The important thing here is that you keep all your notation consistent, and you compute all things always in the same way. The important thing is that as long choose one reference system and use it consistently. Bonus is actually not to do like I did, but to use like z in this direction so that x and y and z form right-handed uh, triad, but that's like additional points. The important thing is that you keep it consistent across your simulation, otherwise things will break. All right, but we can have a break at this point, and we're gonna take, I'd say, about 5 minutes, and I'll set a timer so that you know how much is left for the next part. All right. Okay. Um, we can start again. I just wanted to come back a little bit to um, do a small reminder of the basic equation that we want to work with. So again, it's the solution of Newton's law. Here we have the acceleration, internal forces, which are our elastic forces given by the our springs inside the system, and we also have external forces plus the damping, which is gonna be dependent on the velocities. Now, all these was the basic, and what we want to do now is that we want to try to well, before we go to the analytic integration methods, which is the next part, so how to actually integrate this equation in practice, I want to mention a couple of more implementation notes related to heavy objects, which we will encounter them because some object we will consider them as will have a much larger mass than other objects, and we don't need to model all of them in the same way. And if the mass is really high, typically what happens is that the movement is very limited, and this is something we also have experience in our daily life. And usually it's actually simpler not to even update their position. So for instance, if we have a wall and we have an object that is colliding with the wall, and we are assuming that the wall will hold the collision, then it's not useful to compute the deformation or of the wall because it's gonna be there anyway. So in any case, these there will be the spring forces that will influence the other points, and so sometimes it could be helpful for our model to add to each point a Boolean value to say, okay, this point is fixed and it's not gonna move, and that's gonna actually save us some calculation in general because we don't need necessarily to update the position of these points. So now let's do a little bit more of math, and this is gonna be probably the most painful part of this part of the course. And so, as we mentioned before, these are the equation of motions that we want to integrate. And as we were looking at the Euler step, we want to define the position at a time t plus h. But as we mentioned before, we cannot really do it in an analytical way because our acceleration, which means our forces, internal, external, plus damping, will depend in a non-trivial way on the position and on its derivative, since we have also the velocity. And for this, we need to find another way to do this. So what we do is that we rewrite and classify our equations. So now what we have here, and we've always had that, but we never call it like that, is an ordinary differential equation. And what makes it ordinary here is that we only have one free variable, and which is time, and we have that derivatives we are deriving only with respect to time. If we had forces that are changing in space, then what we would also have derivative with respect to space, and in that case we have two different variables that we need to take into account, and that's gonna complicate massively our ability to integrate these equations. So what we are doing here is that since we have only one single variable that we are deriving with respect to we can rewrite the derivatives in a simplified way. So this quantity here, which is the acceleration, is the second derivative with respect to time, and that we're gonna write it in this way with two I don't even know what they're called. Two two signs, and instead what is now a single derivative is going to mention with a single tick on the side. In general, we can rewrite our expression that making so that our acceleration here, x second, is actually a function of time, which is the free variable, position, which is x, which comes in the elastic forces, and also the velocity, which is x prime. Now, we're gonna do a small change of notation, because this is gonna help us to generalize to different cases. And so here you need to bear with me a little bit. So normally what we have is that in simulation, x denotes the position. So where in space we are positioning a certain part of our body, a certain point mass, or certain quantity at all. In the following part, we are considering x to be the free variable. So in this case, x, the symbol x, is gonna play the role of time. So in our previous notation, the position depended on time. Now we're gonna define the function in this way, saying that our function is now y, and our free variable is x. This is the notation that is typically used in maths to work with ordinary differential equation, and that's because in general we can have that the notation that I've seen before was mostly like a physical one, so something that is closely tied to the real world, whereas typically mathematicians try to abstract further and try to consider a situation in which these, let's say, our free variable is not necessarily the position, the time, and the, let's say the dependent variable is not necessarily the position. So for the time being, keep in mind that x in this sense corresponds to the simulation time, right? So what we have now is one free variable x, and we have a function of the highest derivative of the solution y of x, sorry. Now, we are making some simplifying assumption, in the sense we are only considering one free variable, so there are not many, which also immediately gives us an ODE, so like an ordinary differential equation. If we were more than one, then we have a partial differential equation, and we have a look at it just later. In general, or at least in the previous case, we have seen that the second derivative of our position was a function of the free variable, the actual quantity, and this first order derivative. But in general, this can be extended to first order, second order, third order, whatever order, up to n-1, and then we can write the nth order derivative as a function of all the previous one. This, as we mentioned, is an ordinary differential equation, and the highest derivative here, n, is what defines the order of the ODE. So the previous problem, we have a second order ODE because we were writing y second as a function of x, y, and y prime, right? So in this case, in the more general case, then we can have an nth order of the ODE, and that's gonna give us the more general case, and our integration tools will always apply irrespectively from the order of the ODE, and that's more like a more general description of this equation with respect to the one that we were using before. Now, we can consider, for instance, a visual example of a first order ODE, and then in these cases, what we see is that our velocity field, y prime, is defined as a function of the position and time, and No, okay, yeah, sorry. So if we are following a trajectory, the yellow one in this case, then we can compute in each and every point what is the velocity by evaluating the function f. Although it should be important to notice that the definition of this f function is not limited to a specific trajectory, but it is a function that spans all over x and all over y, which means also that in practice we are able to compute in principle the velocity in every single point in the velocity field, not only along a specific trajectory, and a number of different trajectories can pass uh, through the other points in which, and through all of them we are able to compute what is the derivative, because we have it from the function that we have just defined. Now, in the case of the ODE, we are now referring to a first order ODE as we were looking before. We can it's relatively simple. So in principle, we can try to tackle this in an analytical sense. And just as a reminder, that the y is the dependent variable and x is the free one. And we can write something that looks like this. In this case, what we have is, as you can see, we have this term, which represent y prime, and the function that we can rewrite this as y prime equals yx minus yx minus 4, and that is valid for x greater than 0. And this equation that we have on this side is a function of both x and y. And as you can see, we don't necessarily need to have a specific relationship, because the general definition of these ODE states comprehends every kind of relationship that we can have with respect to x or with respect to y in our equation. We can solve this analytically because it's relatively simple, and I'm just gonna and what we get is a function of y, and this function of y is defined in every point, but it is defined only up to a certain constant c. Why? The problem is that whenever it's in the definition of the derivatives, and whenever you derive a constant quantity, this will have, since it doesn't change, is gonna have a zero derivative, which means that a solution of this equation will tell me let's say, the slope of our curve, but I can have different curves that have exactly the same slope, but I'm not able to tell which one is which, because all of them satisfy our ODE. So what we need to do is that we need to work with this c that is called an integration constant, and in order to determine it, we need to fix an initial condition. And in particular, we can set y of 1 equal to 1, and these allow us to compute c equal 3. Otherwise, we are not able to tell in which point how to fix this solution. Yes? Sorry, which one? I'm not fully sure, but because here we are integrating the equation, but we can look at that also later. Maybe it's an error in the slide. Yeah. So that's actually, and initial conditions do play an important role in the definition of our problem, because what we can, for instance, we are discussing whether what happens to a projectile, but if we are launching it from the top of a building or from the ground floor, then the trajectory that we get is completely different, and is something that we need to keep into account whenever we are solving these equations. So that was the simplest case. Now we switch to a second order ODE, which is the case that we were looking at before. So second order means that, in a sense, from a physical perspective, we are considering the acceleration. And for defining the solution of this case, we need two initial conditions, not only one. So in general, what we need is that, given the order of the ODE, we need, and that order being n, we need n minus 1 initial condition or boundary condition to define the solution. And this is something that we're gonna have a look a little bit later. But so in this case, for instance, not only we need to define in physics the initial position, but also the initial velocity. That gives us a unique solution in which we are able to do this. And in general, this depends on the fact that for every nth order ODE, we are able to rewrite it as a system of a first order ODE. And that's normally relatively straightforward. So what we do is that we just say that the second order derivative, let's say dy dx, is actually equal to the first order derivative of the first order derivative. And then we call this quantity, I don't know, y1. So in this way, we are able to say that this quantity that now we called y2 is actually equal to the derivative of y1. And then, and then we add it here. So now the derivative of y2 is sorry, the other way around. Let me rewrite this in a better way, or more consistent with the slides, so to speak. So now let's assume we have a certain variable y, and we want to write that the derivative of y1 is equal to y2. So now, whenever we have the derivative of y1, instead we can add y2, and then we can write this as a system in which we are including this first relationship that we have written on the first line. And in this way, we have n different equations instead of having a single one of ith order. Yes? So are names that we are giving to our quantities. So let's say placeholders to some extent. So you see that we have our, let me go through the entire thing. So we have the second derivative that is a function of the free variable, the dependent variable, and its first derivative, right? So we want to write this as a first order problem. So we know that y second is equal to the derivative of a certain quantity again, right? So far so good. So like it's just the second derivative, the first derivative of the first derivative, right? Now, if I call y prime equal to what is it here? To y2, and I give it a name, it's just I call it in this way. I see confusion. Because in this way, y second becomes the first derivative of y2. Which effectively means that we are rewriting our expression only using first order derivatives rather than second, third, fourth. Yes. Because in this way, now you have, I'll get there. So now, instead of having one single equation of nth of the order n, you have n equations of order 1. Okay. In general, this helps because you can, in a sense, you are simplifying the problem by increasing its dimensionality. Like you're moving the dimensionality from the order of the equation to the number of equation that you have for the description, but the amount of information is always the same. But it's simpler to integrate, essentially. Yes. Yeah. Order 1 is better because we can develop a method to solve a single equation, a scalar equation of order 1, and then this applies in a trivial way to a system of equation. And because it just imagine, instead of having a scalar position, you have a vector of position. They will follow a set of equation, and we can integrate them all at the same time. Instead, if you want to integrate a higher order problem, typically what you need to do is that you need to solve your nth order equation, will then give you something. By integrating once, what you get the n minus 1 derivative, and then n minus 1 you need to integrate, and so on and so forth. So you either instead of integrating n steps in a serially, what you get is that you can integrate an entire system, and you get directly the whole thing all together to some extent. Yes. No, you have more dimension. Any other question? Right. So we can now describe different problems depending on the kind of conditions that we are given to define their solution exactly. So the simplest problem that we have already seen is that when we have n initial conditions, so let's say we give the initial velocity and initial position of a certain object, and then that's what we called an initial value problem. And instead, if we have boundary conditions that are defined at different locations, now in that case, we call it a boundary value problem. So an example of these that you can that maybe can help you with is like assuming that I'm standing here and I'm shooting a projectile. I'm shooting it with a certain velocity and a certain at a certain position, and I want to know where I'm ending, where my projectile is ending. Now, and this is an initial value problem. Now, if I want instead, knowing where I am and assuming that I want to hit the door, now there are two boundary conditions. One is where I am, and one is where the door is. So this is how we are shooting there. Sorry. So that's the difference between an initial value problem and a boundary value problem. Of course, in general, second one is relatively trickier to solve because it's typically easier to know how the system looks like now, and instead of having to know how it will look like maybe in the future, for instance, where I'm aiming for. So this was like let's say the simple part, and this is gonna keep us busy essentially for the course. But in general, we should aware of the fact that um, we can have partial differential equation in which we have, as I mentioned before, derivatives with respect to different free variables, not only time. And one example, for instance, is a diffusion equation. In a diffusion equation, you have derivative with respect to time and derivative with respect to space. So even if I'm not moving, then the quantity that is diffusing is changing over time. Sorry, over space, because it's diffusion. What happens is that if you imagine you have a certain distribution of a quantity, then let's say a temperature, and you have something very warm, then over time its temperature will decrease, and at a certain time, sorry, at the same time is gonna increase the temperature around it, and these two quantities are completely separate. So it's two different free variables that we are investigating in the diffusion problem, and it's something that we're gonna need to address also later. And in general, in these cases, what you have is that you both have initial condition and a boundary conditions, which are the temperature, for instance, at the edges. Now, we keep on working on the analytical part of the solution, and we take a relatively simple example. As I mentioned before, if a body is large enough, then we can definitely assume that the body at which the spring is connected is not moving. So we consider a simplified setup. We have one spring. It is fixed at the top, which is equivalent to have it linked to a very large body. And well, now we are considering 1D, but of course this could be absolutely extended to 3D, but it's much simpler. And we consider a reference system in which our deformation is given by x, and our initial length is d. In this case, we can write our forces as minus k times x, which is the deformation, and as such, we can write the resulting ODE now, that is the derivative, the acceleration is only equal to the elastic force, which is k divided by the mass in this case, times the deformation. In this case, we are not considering there is no gravity or other forces that are acting in our system. For this very simple system, we can try to solve this analytically, and what we want to do is that we want to find, in practice, some quantity that was the second derivative is the same as the function itself. And as some of you might know, this is what is called an harmonic oscillator. And in fact, if you think about it, cosine is a function that derived 2 times gives you the same quantity, well, with a minus in front. And we can also show essentially how the position of our mass is moving over time, and where is the plot? Right, so the harmonic oscillator in this case is just a cosine function, which means that our position will oscillate around the center position infinitely over time, and this system will go on essentially forever, so there is no variation over time. And however, we can include damping, and in that case the solution looks something like this. And in this case, what we have is a solution that is indeed reducing in its amplitude over time. And the interesting thing is that in the equation we have here an exponential, which is proportional to our damping, and the exponential provides the envelope in which our trajectory is constrained. And as you know, an exponential is a quantity that goes down extremely fast. And so in a very relatively limited time, we're gonna end up having a very small oscillation because the energy is subtracted from the system. Yes. Wait. Right, but let's say the thing is that we are defining x as the displacement from rest. So x um, is already the L minus capital L, so to speak, and that's one. It's an important remark actually to see that the initial length of the spring doesn't play any role. So if the length d is changed, so the length at rest is changed, then the dynamic doesn't change at all. And that's because the forces that are acting on the spring depend only on the displacement. But yeah, like it's if I were to write x as the position, then that actually was the correct statement and correct remark. Yes. The resulting ODE, we obtained it in the same way as we seen before from Newton's law. So we know that our force is k minus x, and we also know that F is equal mx square, the second derivative of x. If I put together these equations, what I get is that mx second derivative of x is equal to minus kx, which by reordering the terms, you get the expression from that. And you can integrate analytically the solution. It's mostly classical way of approaching this problem. And usually you put either a sine, cosine, sum of sine or cosine, or an exponential, and you get that the solution is something that looks like that. Dumping, voila. Question, yes. Mm-hmm. So we can look at it in this way. Okay, if we have a let's assume we have an x tilde, which is our initial position plus our deformation, right? Okay, now if I take the first order derivative, x prime of x tilde prime is equal to the derivative of d plus x. However, d is constant, which means that the first derivative of x tilde is the same as the first derivative of x, which also means that in practice this applies also for a second order derivative, which means that the initial length again does not really play a role in the dynamics, and the two acceleration are actually the same because they are the same up to a certain constant, and even the velocity acts in the same way. So in principle, you don't really need to define an additional coordinate for that whenever you are integrating this kind of system, because the initial length is constant, essentially. On the other end, if you have a system and you are, let's say, we are discretizing a body with small masses, then you really need to take into account, let's say, the global position, and then in that case, you cannot really do the same trick because there will always, like, the initial position um, needs to be taken into account. So this not always applies. You need always to assess critically whether it makes sense or not, essentially. Other questions? Right. So, analytical solution, as we saw before, will gives us the position for any arbitrary time, and this, which is amazing. So, which means that we don't really need to perform any kind of integration, numerical integration, because we don't need, we given a single position of this system, then we know at any single point in time how the system is gonna look like. However, this in practice does not really help us, because it's only useful for extremely simplified settings, and usually this is not what happens in our cases, and it's not in general possible to do this when you have, for instance, a set of springs that are connected in a non-trivial way. So it's something that we need necessarily to resort to numerical integration. And numerical integration is the topic of the next part. I think we can have a break here, and then we resume later, maybe with Felix. We will resume later for a while, and then we will switch to Felix. Good. All right. Um, let's start again. I'm gonna have few minutes more, then I will give the word to Felix. That's gonna give you an overview on the more practical part of the course. As we mentioned before, where we are left is that we're not really able to perform the integration of a second order ODE or a system of second order ODE directly using analytical methods because essentially it gets way too complicated. So what we do is that we resort to what is it? Numerical integration. And to do this, we need to have a little bit a reminder of what we are doing. So first off, we have the target function that we want to compute. X is again the free variable. Y prime, in general, we describe a derivative with respect to x, or for a higher order, even though we will not really see that, is gonna be yn with the parenthesis. H is gonna be the discrete step size in the free variable. So let's assume we have x as a quantity, then we discretize this quantity to be 0h, 2h, and so on and so forth. And then we can start from a general point, and so we have x plus h in general that will indicate the next step at which we want to evaluate the solution. And in particular, we will gonna evaluate yn is gonna be, in principle, we're gonna try to approximate essentially what happens for y it x plus nh. It should be noted that these two quantities are not the same because yn is only our approximation after n steps that are approximated, and that's gonna be fundamentally different from the value of the function evaluated exactly at the variable plus n step. We can see that what we can do to do this is to perform a Taylor expansion. Taylor expansion is essentially a local approximation of the solution starting from the point that we already know. So what we do is that we want to evaluate the variable at point n plus 1, which is, as we mentioned before, the previous valuation plus h. And then we can compute an expansion of such variable in this way. So what happens here is that we are using the derivatives of y to approximate the value in a point that is close by. These can be seen in a more intuitive way by looking at the plot. So, for instance, let's assume we have a certain point x0 in which we know the solution being x, y0, and then we want to advance of a certain amount h, and this way we arrive to position x1. Now we can simply move further, and in this case what we are doing is that we are approximating with a polynomial of a function of h in order to find our approximation of the solution. Bear in mind that whenever we are computing this kind of expansion, this quantity, typically all breaks, that's really true. These quantities are evaluated at the position xn, meaning that these quantities should be treated as constant. And here, the only variable, also this one, is a constant. So what happens is that here our solution looks like something like this, which is essentially a polynomial value with respect to h. So it means that we are approximating the function essentially with a certain and given polynomial. And as you can see from this plot, the resulting position that we get from this expression is not the value of the function of the original function, but just its approximation. And whenever we are moving forward, we are always starting from a point that is not the correct one, because we don't really know the solution in this point, right? This is something that we are trying to approximate in the first step, but then to build the second step, we can only rely on this point that we have just computed, which means that there will always be a certain degree of error that we are introducing whenever we are performing the computation. And of course, this is not always like we are not always overestimating or underestimating, but it's gonna be a reasonable mixture of the two, depending on the values that we are getting each and every time step. So essentially what happens is that we are moving back and forth, and we are trying to approximate the function as best as we can. And one important element and question could be how well we are approximating this function. And the solution, the answer to this question, is given by this last term, which in mathematical terms means that in this expansion is correct if we consider an infinite number of elements. So this equation holds exactly if we have the sum for let's say e that goes from 1 to infinity, that goes from 0 to infinity of the derivative of the ith derivative in the position xn divided by e factorial times h to the power of e. So if we are using an infinite sum, then this equation is correct, so it's perfect and there is no approximation. As soon as we truncate, so for instance in this case we are considering e up to 2, then this term is called truncation error, and this would give you essentially a ballpark in which we have in which the terms that we are not considering are playing the role of these terms into the expansion essentially. So we know that our error here is going to be proportional to the power of 3 of the size of our discretization, meaning that if we reduce this discretization by a factor of 2, then our error will be reduced by a factor of 8, and so on and so forth. Yes? On which side? On the left side is the same as above. So it's like n plus 1, so like the position plus the movement to the side by h, essentially. This is important to consider, because depending on the truncation error and depending on the error that we can have a bunch of problems that can come up. So for instance, let's take this plot. Here, if we were able to integrate exactly following the gradient lines, then we will go round and round in a perfect circle. But as you can see, because of the integration error, then our solution is getting off track and going farther and farther from the center each and every step. And importantly, if you consider a smaller step, like in the second case, then you see that the time at the velocity at which we are diverging from the center is lower. That's because we are making an error that is smaller because of the finer discretization, and that's something that you are going to balance in every simulation that you're doing, because you want it to be as accurate as possible, but at the same time you want it to be as fast as possible. So you cannot have a game in which people needs to wait 10 minutes to see the next frame, because even though that's gonna be like as accurate as it gets, because that's kind of gonna ruin the game to some extent. So you need to find a balance between accuracy and time to solution, and that's something that is always gonna be always a problem. And another problem that you can get is these interesting oscillation problems, especially when your solution or your gradient field is a little bit weird or doesn't really look very regular. So in this case, it's very interesting in my opinion, because the solution, you can see it's diverging and the exploding, and that depends on the fact even this is happening even if the h, so the step, is constant, because here, since we have a very small valley in between, what happens is that we are moving to a point in which the the derivative is larger. So the next step is gonna be larger to a point that has a much larger derivative again, and these has diverging dynamics. So our simulation essentially is gonna explode if we are using a step that is not small enough, or if we are using integrators that are too simple and they are not able to, let's say, counteract this effect that are all numerical effects. Of course, the practical solution is just add numerical diffusion, but this is something that should be used with a grain of salt, so to speak. So like, try not to abuse of these tools, because then eventually your simulation will anyway show that you've been trying to cheat the physics in order to have it converging. All right, but at least for me, for today, it's more or less it. Is there any question that comes up now? Otherwise, we're always available also later. So the thing is that in general is not that you don't have these. Here we can have a plot with x and y, and that's very simple and easy. But for instance, if you have a system of springs, you will not have a clear picture of what the gradient and what the field will look like. So you cannot really do it a priori in general. So it's something that you will see your simulation is gonna like start diverging more in a let's say empiric way, so to speak, and then you need to see how like to reduce the step size or change the integration method. All right. Now just give us 5 seconds to optimistically 5 seconds to switch from. I'm pretty optimistic.
Test, test. Oh, wonderful. Okay, 1 second. Still not it. 1 second. Here we go. Okay, now we can start. So, good morning, everyone. My name is Felix Köhler. I'm a PhD candidate with Professor Ture, and I'm a colleague of Dr. Guastoni, Dr. Winchenbach, and you will also soon meet Dr. Lino, who do the lectures this semester. And I will be responsible for the administrational side of that course, like asking questions on organizational aspects, organizing the programming exercise, and so on and so forth. And today I want to introduce you to this programming exercise that goes alongside the semester. Yeah, let's talk a little bit about the goals. So why do we do that? So yes, immediately a question. Yes, both. Okay. I hope the questions will be answered afterwards, and then we can do more Q&A. Okay, so first start with the programming exercise. So in this course, as you also learned today, there are a lot of theoretical aspects, can be quite abstract, and we designed this programming exercise to guide you along in the semester to really get a practical understanding of all these topics. I'm really not that good with the microphone, unfortunately. Okay, no, that should be better. Cool. So I think the very important translation that we want you to be able to achieve is going from the math to actually coding it up. And I started being this TA for game physics 3 years ago when I started my PhD, and then I also did these programming exercises in preparation for the course, and I actually really enjoyed coding them up. It feels so amazing doing these interactive simulations for mass spring systems and also for the other topics. And this is a very nice way to really learn about that. And of course, on top, we also want to foster teamwork among you, such that you can collaborate, exchange, and this was also my experience. I exchanged with people about this programming exercise, and that helped me a lot also understand that. I think back in the days when I created these slides, I read something on Twitter which said I did not properly understand something before I can teach it to a computer. You can easily fool a human, but it's very hard to fool a computer. So being really able to implement all the algorithms we present to you in this class, I think is extremely valuable. And moreover, also we see that the people who contribute to the programming exercise do usually perform the best during the exam, because really doing this hands-down experience helps you with preparing also for the exams, getting a feeling for the algorithm. So how does that work? So we have a very simple scaffolding project that is a 3D rendering engine with very simple drawing commands, like being able to draw spheres, being able to draw cubes. It is based on C++ and uses WebGPU-based rendering. In case you haven't heard of that, it's a very modern framework that also allows us to run across multiple operating systems. So far, we have tested it with Linux on GCC compilers, on Windows with MSVC, and on Mac with Xcode. So that should probably cover, I'd say, 99% of all students, in case you don't have a very exotic setup. Then this template also comes with typical math utilities based on GLM. So that's a library for, well, usually originally for OpenGL, for the mathematics utilities, providing you with quaternions, matrices, and vectors that you're going to use for this particular exercise. This is new. So in case someone is here in the audience who did the course last year, might see that this is not how it was last year. So last year we had a very old-fashioned Windows-based, DirectX-based, Visual Studio-based framework, very much beloved by all the students who did the exercise. And we changed that in an effort during the summer semester. And I'm actually very happy with how this turned out. I will also show it to you on a live demo in a second. But this comes also with some issues, potentially. So we battle tested it a lot on a lot of OSs, a lot of configurations, but very likely you're gonna run into some issues. Then it's very important to let us know so that we can improve that. So especially also because WebGPU is this new framework. So we're very much interested in how it's gonna turn out, but I'm very optimistic about that. So you can either let us know via Zulip, the student forum on Zulip, or directly open an issue on GitHub. Or even better, if you are very experienced with this particular C++ environment, then you of course can also open a pull request. So how does this programming exercise look like? So we have 4 structured programming tasks which you have to do in groups. And then afterwards there is another task which is more of an open project, where we want you to become a bit creative, combine some of the aspects that you saw in the previous exercises or something you saw outside of the course, and create something more grand. Of course, still in the constraints of the course, but show you that you can go beyond the exercises. So I will show you the template project in a second. For all the 4 exercise sheets, we will have, so for all the 4 programming tasks, we will have exercise sheets that will guide you on what is to do. They also have clear deliverables on what you have to implement. As said, the open project is a bit more freely. Usually these deliverables come in the form that you need to implement a certain situation, a certain scenario. We call this a physics scene. You will also see that in a second. And then usually you have to implement some interaction. So you gradually start by first doing some terminal printouts, then some static simulation, then ultimately interact with mouse, keys, and buttons. And this is, I guess, the big learning I had 2 to 3 years ago when I did the exercise, to really see these algorithms in action. And we also had the question earlier, for instance, what does that mean with instability? And I guess you get a really good understanding of what makes a certain algorithm stable or unstable by just exploring it. So again, another encouragement to work for this programming exercise. So there will be groups of 3 to 4 members. So to foster this team collaboration aspect, you will register via Moodle. I just opened the registration portal on Moodle, but don't have to do it now. You have a week time for that. I hope you maybe already know a couple of people you want to work together. If you don't have someone yet, then please open a thread on Zulip, or there's already a thread open where you can ask for team members, and especially also for those maybe exchange students, that's a nice way to find new team members. Okay, so what are the concrete requirements? So there will also be a reward. So in generally, doing the programming exercise is optional. So you don't have to do this. You don't have to do it to pass the course. But there's the material reward, which is a grade bonus by 1 grade level. So either 0.3 or 0.4, depending on what you end up getting. And the immaterial bonus, as I already mentioned, is that it prepares you for the exam. And I guess like, what do you take away from a course? And it's always very hard to say, well, what did I took away from the lecture? But if you really coded something, this is a great experience. And I guess this is something extremely valuable. Okay, but let's go through the details. So what do you have to do? So you have to submit source code to Moodle in time. So this is for all the 4 exercises and the open project. This is supposed to be a zip package of your source code files. Show this to you in a second. It will be under a specific directory in our scaffold project. Of course, don't submit any executables, just the pure source code. Also no GitHub repository links, really just the pure source code. You should not use any libraries beyond what we give you. This is more than sufficient to do all the exercises. Of course, if you encounter any very big errors, then let us know, but we try to battle test it as good as possible. You shall not modify the rest of the template. And of course, obviously, your submission needs to solve the required deliverables. This is the first point. The second point is that towards the end of the exam, the end of the semester, you have to pass an, in quotation marks, oral exam. This is not as difficult as it sounds. So in that we will create executables based on your submitted source code file, and then you basically will be presented with a laptop on which your submission runs, and we will ask you some questions. So for instance, do this, what do you see here, why can this be explained? And usually if you contributed significantly to the code submission, you will pass the oral exam easily. So we only have a handful of students who do not pass. So that's, if you work on the exam, that will be super easy. It's not a big hurdle. I said also around only 15 minutes. And then the last requirement is that you need to present your open project in the last lecture. So this is right before the semester break in the beginning of February. And in there you should do very small pitch about what you did, 2 to 3 minutes. I guess if some of you are familiar with the demo day of the games engineering course, then it's probably in a similar format, maybe a bit extended. Then I think there you only get 1 minute. Okay. Then what kind of exercises do we have? So last week Dr. Winchenbach already mentioned that you should look out for team members. So this is probably why I said your programming topic is find group. Then this week we will have an introduction task. This is to make you familiar with the programming template. This is to be done in individual submission, and it's also super structured. I will also share the slides afterwards, in case, great. So this is just follow along a guide. There's not much thinking, just reading and copy pasting. Thereafter, we have the actual tasks. These are then supposed to be done in groups. So the first task is on the mass spring systems, which Dr. Guastoni today talked about. Then we have 3 weeks for a task on rigid bodies and 2 weeks for a task on PDEs. And that should then be done before the Christmas break. And then in January, you have time to work on your open project. And as said, the last week is going to be the presentation for the open project. And then we have this, in quotation marks, oral exam, which will either be in the last week of lectures or the first week of the lecture-free period, but we will let you know in advance. Of course, there is support, and this also comes to your question. So, so far, mostly I talked about the programming exercise, which is this optional thing to do alongside the course, which gives you the grade bonus. Then we also have tutorials, and tutorials come with tutors, but not, and we have tutorial worksheets, which are like more, let's say handwritten, do a little bit of an integration, do some math on a piece of paper type of tutorials. And but we don't have tutorial worksheets for every week. And if there's no tutorial worksheet, like this week, the tutorials are meant as Q&A sessions to help you with the programming template. So also like today. So we have 2 tutors available for you. 1 second. The first tutorial will be on Mondays from 6:15 to 7:45 from Nick Christodoulou, and another one will be Tuesdays. So the first one there's also tomorrow morning from 8:30 to 10. These tutors will be available in class, and when there is a week with tutorial worksheets, they will present or show you solutions to the worksheets or interact with you on solving the worksheets. And as said, if there are no, then it's mostly a Q&A session. Okay, please. So repeating for the recording, so if these tutorial worksheets, do they contain questions which are similar to the exam? Yes, to some extent, true. But of course, towards the end of the semester, we will also provide you with a sample exam, such that you get a feeling for the exam. Yes, so answer this question, the exam will be more handwritten and probably less programming, but in my experience, doing the programming reinforces how to do the hands-down calculation on a paper. Yeah. This is, I cannot fully answer yet. I think that's probably best to open a question on Zulip, and then we will come back to that. Yeah. Oh, yes. Okay, sorry. That's a good point. The tutorial sessions are not recorded. They are in person. But we will make some recordings of similar tutorial sessions available also on Moodle in case you want some digital recordings, but they are in content a bit different from what we have in the tutorial worksheets since they are a bit older. Yes, please. So there's a schedule posted on Moodle that you can look at, and if there is, if it says programming support, then there it is meant for this Q&A session. But oftentimes, so usually when we have the tutorial worksheets, they do not cover the entire tutorial, so there is still time for also a programming Q&A, and you can of course also use other means like Zulip to get your question answered. Or it's of course not ideal. You technically could also email the tutors. I would possibly recommend you to ask on Zulip, because if you ask on Zulip, then everyone benefits from an answer. But that's another way to get your questions resolved. Yes, please. Yeah. Technically, you can ask anything. So I guess probably in the beginning, mostly people have issues with the programming template. Towards the second half of the semester, people might have more questions towards the exams. So that's a bit more flexible. Yeah, please. No, please. So the yes, of course, yes. One likes to be ambitious with that, but I would recommend you to stay within that. Of course, if you have any meaningful enhancements, we are open to potential pull requests. But of course, we try to maintain this, or like to want to have this template as simple as possible to have everyone be able to use it. Yes, please. That's primarily for us to ensure that there's a deadline. So yes, of course, you could maybe do this with Git tagging, but this is usually just, I would say, the easier way for most students to submit the code. Please. It's going to be a programming support. So I will show that in a second for the first programming exercise, and then let's go to that, and then we can ask answer the remaining questions afterwards. Just to finish this slide, as mentioned, the other forms of getting support is the Solib forum. Here, I would also encourage you to be active and answer other students' questions. In my opinion or my experience, it's always nice if you have to explain it to someone who is like currently struggling with understanding. I think this is, very beneficial whoever answered the question. And then, of course, I already mentioned that, so we have the template on GitHub. So if there's any fundamental issue, of course, open issues there, GitHub issues, or if you already have a solution, also feel free to open a pull request. But this is all optional if you are familiar or can use GitHub to that extent. Okay, cool. Let's take a look at the template. That's a live demo, so I hope that will work. Okay. Okay, I have to mirror the screen, I guess. Let me see. Cool. Yeah, that works so far. So this is our GitHub page for the game physics template. So I will start by cloning it. So here I simply clone it with HTTPS. The link to the template is, of course, also on Moodle and on other places. Let me make that a bit larger. So let's clone the template. And then we recommend you to work with Visual Studio Code. I guess it's probably by now the de facto industry standard editor, at least to my experience. Oh, I'm sorry, it's very slow, the ED-ROM here. Sorry? Yeah, but it's okay. We can wait that bit. Okay, so we would recommend you to use Visual Studio Code because it already comes with all the utilities or extensions that might help you easier work with the project. Okay, here we go. So let's take a look. If you start that, so right now here I have a couple of. Let me maybe increase the size of it. So I have Visual Studio Code extensions installed for C++ and CMake. So CMake is a build system that we use to ship with this game physics template. So once you have these extensions installed, this Visual Studio Code should recognize that this is a CMake project, and then you can use a toolchain. So for instance here, I use this particular toolchain, then Visual Studio Code should already automatically set up the project for you. That should take a bit. Let's see. Should not be too long though. Maybe in the meantime I can quickly talk about the directory structure. So on the left hand you have this folder, it's called scenes. And within scenes, that's basically your playground during the programming exercise. In there, you're supposed to create your source code. You are free to structure your source code however you want. The only important requirement is that you implement scenes, what's what we call like the solution to a particular deliverable on the programming exercise worksheet, and then register these scenes. I will also show this to you in a second. And then essentially when you submit your source code, you will take all the files that are within the scenes directory and then package it together into the zip code and into the zip folder. Okay. Let's hope that this finishes soon. Okay. Generally, maybe beyond that, let me give you some other advice. So there's the README, obviously, and in the README you find a lot of helpful tricks how to use the template. I would also recommend you to obviously read through the README. Then, how's it doing there? Not that well, but should be going pretty soon. And then the very first programming exercise, or the 0th programming exercise that is done, supposed to be done this week, is based around a guide. So there's this guide markdown file that you can also obviously read on GitHub if you want. And your task for this week is to basically work through that guide. So this is should be a step-by-step instruction to set up a very simple use case of this particular template. So as I already mentioned, there's not much thinking to be done this week. So it's primarily you can, if you want, copy paste all the snippets that are in the guide. Yeah, you can copy paste all the snippets that are in the guide, but it's just that you see all the aspects of the programming template. Why is it not going that fast? Let me quickly check if that. Well, that should actually be quicker. Either way, so I don't know why it is so slow, but usually when you then configure your CMake, you can then compile and run the project, and this should technically bring up a blank 3D rendering with an wire cube, and then this is basically the starting point from which you then are supposed to do this guide. I will show you the solution to the guide, and let's see. Hope that, okay, that one worked. So here it is already configured. So essentially what this is how this template looks like. It's a very simple 3D rendering engine. As said, this is the demo scene here. The demo scene only contains this wire cube. I have implemented this scene that is associated with the guide that is on the GitHub page, and this is essentially a cube which is rotating fairly slow. You can use a GUI to interact, for instance, to say how fast it should be rotating around its yaw axis, or have it rotate in the other direction. And you can then implement some simple interaction to launch spheres out of the cube, and also see how they are state managed to eventually also be deleted. And you can also interact. So now I'm using the space bar to shoot as many spheres as you want, and that should get you familiar with all the methods that are within this template project to then get you started on the actual programming exercises. Okay, I will close that, and still don't know why it took so long with the configuration. Okay, let me switch back to the presentation. Cool. So as said, I would recommend you to work through this programming exercise 0, and there it also on Moodle there's the PDF sheet on how to submit the solution. So as said, this will be an individual submission this week, so there's you just submit by yourself, and then from the next exercises on it's gonna be in groups. Okay, I have a video here which we should skip because it's just a backup. Essentially, this will also be described in the guide, but I just want to highlight it once again. So we have a base scene class, and then essentially for each deliverable that is within a programming exercise, you're supposed to subclass from that scene, and then you have methods that you can basically override to implement your specific simulation logic on simulation, on rendering, and how to interact with the GUI, but more about that in the guide. Before we come to the questions, I want to give you some recommendations. So as said, this programming exercise 0, I find it very helpful to get you familiar with the template. I would recommend you to obviously use Git. So if you clone it from GitHub, it's already coming with Git, and I guess most OSs should by now have some Git installation in some way. Then, since it is a group work, it's of course important to meet and communicate. I would of course recommend you to not do the task on the last minute. This is just a recommendation. And very important with regards to the oral exam is that every team member should work on all the exercises, and then you basically merge your solutions. So this has multiple reasons. So the first reason is that of course everyone is familiar with the tasks, and this is helpful for the oral exam. And on the other hand, it also gives you this opportunity to merge your code, think about your implementations, and so on and so forth. And in this regard, I would also recommend you to avoid code sharing tools. So for instance, that you, I don't know, meet and use these live features from VS Code. One is coding, the others are sitting next to it. Because over the past years, we had a couple of times, usually those are the people who fail the oral exam, who just sit next to their team member and let the other team members do, because usually we are somehow able to catch those people with the correct questions during the oral exam. But if you implemented the code, you should be able to answer those questions. Okay. And then the last requirement, when you submit your source code, make sure that it compiles with the vanilla game physics template. So probably an easy sanity check is once you have packaged up your zip file, make another clean clone from the GitHub, just paste in your source code files and see if it compiles. And if that is fine, then very likely everything is also fine for the submission. Okay, so that's the end of this programming exercise introduction. One reminder is, don't forget to sign up for a group. I've also set another reminder towards the end of the week. And I would also highlight that we added a survey on your experience of using the template, like in this first week, how you get through the guide. That would be also extremely valuable for us to what we should potentially add to the guide and improve the experience for the next years. Okay, is there any other questions you have? Yes, please. Okay, good question. So the question was which C++ version we're using. So I think the template by default sets it to C++ 17. I guess that's reasonable. If there's any other follow-up question on that, I guess on Zulip, then the developers for the programming template might be better to ask and help. And any other questions? Okay, if there are none, then just a reminder, today in the evening there would be the first tutorial in case you want support on setting up this programming template. The tutors can help you. Feel free to reach out on Zulip, and thank you very much for your attention. Good luck with the programming exercise.